So we're doing 2.3, and I just want to do a lot of examples for all the rules we wrote down last time. The limit as x goes to 3 of the square root of 16 minus x squared. Okay, this one is a root rule. Okay, let's do a difference right here. So the limit of this limit x is 3, 16. Subtract limit x goes to 3, x squared. Cool. This is a constant, so this limit will be 16. On this one, we'll use that power rule. Alrighty, this part. Okay, 16 minus limit x goes to 3x squared. Okay, then you've got that linear function right there. Minus sign. I'm tired today. Root of 7. This was cool. Next example. X goes to 2 of x. Let's see. X goes to 2 of x cubed minus 2x. Let's start with the sum and difference. Limit x goes to 2 of x cubed. Subtract the limit x goes to 2. 2x. Plus the limit as x goes to 2. All right, so right here, this is a power rule that we can do. This one will do that constant multiple and bring the 2 out. And that's the constant, so we'll take that limit. Okay, inside limit x goes to 2 of x cubed minus 2 times the limit of x, so x goes to 2. And then I'm going to put plus 7. All right, that's your linear function. So this will be 2 cubed. This is also, this is here and there. So minus 2 times 2 plus 7. 8 minus 4, add 7. So 4 plus 7 is 1. Cool. So I have some notes about polynomials in, okay, 1 second. Polynomials and rational functions, but we're going to pause really fast. Okay. Okay, I think it would be good to do this PAL announcement. So let me see if I can go to share screen. And then Christian, if you want to, oh, hi.
Hi, Professor. If you want, I can make the announcement some other time. Because I know you got started with lecture, so I don't want to.
Oh, no, I forgot. I forgot about the announcement, but it's important. So go ahead.
Are you sure?
Yeah, that's cool. That's cool.
Yeah. Okay. Awesome. Okay. Cool. Good morning. My name is Christian Bolaños, and today I wanted to encourage you to take a PAL. First off, what is PAL, right? The program they help you succeed in your courses. In this case, we want to succeed in Calc 1. Help you succeed class. You work with your peers to strengthen your. Now, in this one unit that we offer, there's homework. There's no twice. I took one for Calc 1, Calc 2, and it was very helpful. I did. I'm not guaranteeing that you're going to pass one with an A if you join PAL, but it's definitely going to help your chances. Research shows that students who join PAL bump their grade by half a letter grade. So for example, if you join PAL, you could be receiving a B plus instead of a B, right? Semester. My advice to you is to try it. Like just because you sign up for PAL doesn't mean you have to commit to it the whole semester. Just sign up, try it, and if you don't like it, you can always back out, right? If you don't like what you see, you can always back out. There's no repercussion. Let's see. And now the important question: how do I sign up, right? Let's see. Professor, is it okay if I share?
Chat. Sorry, break it up a little bit. You've actually paused.
Okay.
Okay, you're back though.
Okay. Was I like? Could you hear me at all or no?
Oh, you've just cut out for a moment.
Okay. I wanted to ask if I could share my screen to share like where they can sign up and stuff, if that's okay.
Sure. It should be good to go.
Okay, awesome. Thank you so much. Here we go. Cool. So you can so the are located on the left. Are you able to see the screen, Professor?
Yes. Yeah, it looks good.
Yes. Okay. Perfect. So the times that are listed are here. So Monday, Wednesday, 10 to 10:50 a.m. Another one Monday, Wednesday, 12 to 12:50, and then Tuesday, Thursday from 12 to 12:50. So those are the times that we are offering if you want to join PAL. And again, let's say these classes don't fit with your schedule. The link that's provided right here, I'm gonna post this link in the chat box. So if you want to, and then the link is also how you join. And then I will, Professor, I will email you this like little flyer. So maybe you can share with your students if they want to sign up.
Yeah, I'll send out.
Awesome.
I'll send out that email.
Perfect. And then this email that I'm going to share with you, there's a way to contact the PAL program through email or phone number. If you can contact them and ask them like, hey, I want to sign up, but you guys aren't offering class that's available to me. So what you can do is ask like, is there a way you can open up a new class? And if we get enough students to open up, and we just depends on how many students we get. And then depending on how many students, we can open up a new section to get a whole new section open for you guys if these classes don't work for you, right? So yeah, I will share the link to join. It's very simple. And then I will also share this flyer with your professor, and then maybe she can share it with you via Canvas or discussion board or something. Cool. So let me stop sharing. And let's see. Yeah, I think that's it. That should do it. And then I'll post the email link in the chat, and I'll also send Professor the flyer. Okay, so I think we got some. Perfect. Oops, I did it privately. Any questions from you guys from me? Questions?
Do you have any
No? Okay, sounds good.
I
Oh,
asked you
yeah, go ahead,
privately.
sorry.
I asked you privately.
Oh, gotcha. Okay, I thought that was, okay, perfect. Yeah, I'll just send my email to everyone if that's okay.
That's okay.
Awesome. You can contact me or the PAL program, doesn't matter, and then we will definitely get back to you. All right. All right. My email's posted on there, so feel free to email me with any other questions that you might have. Okay, awesome.
Thank you, Christian.
All right, thank you. And good luck, guys, this semester. You guys are in good hands. Awesome. All right. Bye, guys.
And I'm going to take back over. Okay. So yes, I will put out a little info about PAL, but let's go back to doing notes. Okay, so let's just go into let f of x be a polynomial function. Okay, such that a is in the domain of f of x. Then the limit as x goes to a of f of x equals a. Let me see, it's f of a. All right, similarly, for a rational function, well, I called it f of x. So we'll write f of x is some p of x over q of x. So some polynomial over this polynomial, we'll write that down. P and q are polynomials. Okay, and a is in the domain of f of x. As x.
You're muted right now. We can't hear you.
Thank you. And okay, we're gonna make it through these notes. It's over x plus 5. Okay. So this is your rational function. We can put in -1. The only value that's not in this domain is -5. So let's put a -1 here. And here. One.
We're still part of 2.
And we're in 2.3. Yeah. So actually, that's all we're doing today is 2.3. Let's do another one of these. Okay, the limit as x goes to 2 of the cubed root of x squared plus 3x minus 2. First, we're going to do power rule. Yes. So the cubed root. Let's go. The limit as x goes to 2. X squared plus 3x minus 2. There's like a 1/3 power. So now you can just put in 2 in that polynomial there. Okay. 4 add 6 take away 2. This is cubed root of 8. Nice. I have more examples. Okay. Okay, so the limit as x goes to 3 of f of x. Equal to, so I ran out of room, but this continues right here. This is equal to the limit as x goes to 3. And we have x squared minus 7x plus x squared minus 7x plus 12 over x minus. So part of the problem is that 3 is not in the domain of this rational function, but we'll just go ahead and see what happens if you put in 3. All right, so this would be a 0 over 0. So if you have something like this happening, sorry. Reading a question. So there's a question about approaching from the left and the right. I don't quite understand the question. I'm sorry. I'm going to keep going through these notes. So we have to do some more work on this. X is the set of X in R. X exists in R such that X does not equal 3. Just a reminder that this means exists in. Okay, so what we do is we factor this x squared minus 7x plus 12 factors into x minus 4 times x minus 3. And it's over x minus 3. All right, we can reduce this x minus 3 over x minus 3. Take the limit. X goes to 3 of x minus 4. And then put in 3. Okay, so I'm going to write down how we were able to do that right there. So it's replacement rule. We'll put it here. If f of x is equal to g of x. For all x except possibly at a, let me write that better. Then the limit as x goes to a of f of x is equal to the limit as x goes to a of g of x. Okay, we're gonna do. Oh, also we want to note that I forgot a little piece. Replacement rule if f of x is equal to g of x for all x such that possibly a, then this is equal to this when this limit exists. Put that part. Okay, now let's try. I don't have an example. Well, we just did one. Next, what I have is like little hints on how to find limits, and then then we can do something else. Okay. That's speller. Yes. Okay, try factoring. You can try multiplying by conjugates. Or you can combine fractions, that could help. And that's it. So someone asked about the rule. I'm going to read through it again. So if f of x equals g of x, okay, f of x equals g of x for all x except maybe at x equal to a, but every other value of x is fine, then the limit of f of x equals the limit of g of x when that limit of g of x exists. So as long as this is a, as long as this limit exists, it is equal to that limit you were looking for. Okay. My next topic is piecewise functions. Good. Here. All right, so a piecewise function. One word, yeah. Say function. Is defined in pieces. Let me see. Defined in pieces across a domain that is broken up. So, it's a function that. Let me see. I think that works. Piecewise function is a function that is defined on a domain that is broken up into pieces. Okay, so this function has negative 2x plus 1 if x is less than or equal to 0. Let's switch this over. Put this. Or cosine of x if it's between 0 and pi. Last part is x if x is greater than pi. Okay, let's do this part first. So between 0 and pi, we've got cosine of x, which starts at +1. let's make this positive. Pi is like 1, 2, 3, somewhere here. -1. Open circle, and then cosine, and open circle here too. All right, let's go back here. -2x plus 1 if it's less than or equal to 0. So that starts at an intercept of 0, 1. So now we can fill this in. And then it goes -2 for the slope. So you would go down 2 over 1, but we're going this way, so up 2, back 1. Good enough. Just a line. Okay, here, if x is greater than pi, the function x. So that starts at the origin, goes up 1 over 1, and we'll pick up right here. All right, well, we've got this cool graph. Let's do some limits. Let's find first the limit as x goes to 0 from the left. So that's the symbol to approach 0 on the left side. It's a minus sign in this spot. Okay, we're going to 0 from the left side. So it's this part of the function right here. It's the -2x plus 1. Oh, cool, and we've got an answer. And that's going to equal 1. Let's do the right side. F of x. Okay, when you go to 0 on the right, now you're taking the limit as x goes to 0 of cosine of x. And that's also 1. So the limit on the left matches the limit on the right, so we can just write that the limit as x goes to 0 of f of x equals 1. All right, let's take the limit as x goes to pi from the left. Okay, so that would be the limit as x goes to pi from the left of cosine of x. It's -1. Okay, let's do the limit as x goes to pi from the right. Take this limit, x goes to pi, right side. So that's where you had the function x. And this means that the limit as x goes to pi does not exist, since the left limit didn't match. Oops, wait. The left limit didn't match the right limit. Cool. Let's do something different. So try this one. We're doing a limit. The limit as x goes to 0. Absolute value of 2x over x. Okay, this will work out approaching from the left and approaching from the right. We'll wait for this stuff like that. Okay, so this will be a positive number. The absolute value of any value is going to be positive. And see, put down 0 on a number line. You're going to 0 from the left side, so you're a negative number. So a very small negative number. Over like positive. How did I write this? Oh, I'm doing this not quite right. It's a small positive, small negative number. This is a positive number, and what you're going to get is positive 2. Wait. Negative, that's a positive. Okay, negative 2. Let's do limit x goes to 0 from the right. So 2x. X. Okay, so now this is a positive number. That's a positive number. This will be positive 2. Okay, which makes this limit does not exist. So I think it will help if we write this function as a piecewise function. And I did draw a graph. Okay, so f of x equal to f of 2x over 2 equals. Let's see, I'm trying to think. We want to stick with this example, but after this, I'm going to put a reminder about absolute value functions. Okay, so it's going to be (2x over 2 equal to 2). If x is greater than 0. And it's the negative of 2x over 2, which is 2x over x. And you can't have 0 in the denominator, so it's not going to be in your domain. Let's graph this. Okay. If x is greater than 0, it's positive 2. If x is less than 0, you're at negative 2. And I think that's it for this example. So I want to write the absolute value function down. Okay, the absolute value of a is piecewise function. Either it's positive a if x is greater than or equal to 0, or if a is greater than or equal to 0. Negative a if a is less than 0. Anything else? I do have another example. So we'll do absolute value of 2x plus 3. It's 2x plus 3 if x is greater than 0. Or it's the negative of 2x plus 3. Something's making me question this. I want to check this really quickly. I have a feeling that this might not be quite right. Oof. I think I might be trying to just jump past the problem. Oh yeah, there's a problem. So let's work on this a little more. So this part, and then that needs to sit there and be greater than or equal to 0. So we'll solve that with like some scratch work. I need 2x plus 3 greater than or equal to 0. Okay. 2x greater than or equal to negative 3, x greater than or equal to negative 3 halves. That's what you would put here. It's 2x plus 3 if x is greater than or equal to negative 3 halves. This part or negative. Okay, let's do more scratch work. This time I need 2x minus 3, 2x plus 3 to be less than 0. Yep. Let's do 2x less than negative 3, x less than negative 3 halves. Okay, that's it for that. So we want to go on to talking about limits that go into infinity. All right, so I have an example. It's the limit as x goes to 3 from the right. Of x is x squared minus 6x plus 10 over x minus 3.
You're on mute, Professor.
Okay, thank you. Okay, so numbers that are close to 3. So let's say that this is close to 9, and this is about, let's do like this, 9 minus 6 times 3 is 10 over, what I have here is, the right side of 3, so something like 3.999. And that difference will be a positive value. So this is a positive small number. We've mentioned this
Would be
before.
like a positive.
Yeah, it's positive. Oh, positive small, so positive big or positive infinity. Okay. Next is to just do this limit, this function, but approach 3 from the left. So x minus 3. Okay, so on the left of 3, it's something like 2, let's see. Oh, I think that other value I wrote would have been, but a closer number would have been 3.000001. That's something close to 3. Something close to 3 on the other side would be like 2.99999. Okay, now we're putting values like this into this denominator. So you get out some kind of number over a negative small value. So it's a negative big. Okay. I have one more. Actually, just to wrap this one up. So the last thing to say is that the limit as x goes to 3 of this function x squared minus 6x plus 10 x is 3 does not exist. All right, so that's it for examples. I've got 2 theorems to write down, and then we can call it a day. First theorem. Let's put it up here. If f of x is less than or equal to g of x, for x near a except possibly at a, and the limit of f of x and the limit of g of x exist. X goes to a, f of x. Just put the word and. Limit x goes to a, g of x exists. Okay, so read through it. F of x is less than or equal to g of x for x near a, except possibly at x equal to a. And you know that the limit of f of x exists and the limit of g of x exists. Then the limit of f of x as x goes to a is less than or equal to the limit of g of x as x goes to a. Okay. So the next theorem is similar. It's called the Squeeze Theorem. And we're going to draw a picture at the end, hopefully. All right, let's see, I've got f of x less than or equal to g of x less than or equal to h of x. For x near a. Except possibly at x equal to a. And the limit of f of x exists, the limit of g of x exists, and the limit of, limit of each exist. Yeah. Limit x goes to a, f of x, limit g of x. Then, also. And you know the limit for f of x and h of x. So we'll write limit x goes to a, f of x equals L, and it's the same thing for the limit x goes to a, h of x. Okay. Then the limit as x goes to a of g of x is also equal to L. Okay, so we're going to draw what's going on. You've got, so this is A, and we'll call this, we'll just draw our functions first. First function, we'll go f of x down here. G of x is greater than or equal to f of x, so this is like this. And then h of x is greater than or equal to g of x. Okay, so your values near a, and let's see, let's get this actually. Let's call this L, and actually this function, as this function approaches a, its limit is L. So let's get a little closer to L right here. And then this function too, this function was supposed to have a limit of L as it x approaches a. And we have got this function squeezed in between, so its limit is also equal to L. That's the end. So I'm pretty sure we just finished section 2.3, and we've already done 2.4, which means next time we go to 2.5.